Okay, hello everyone. Some of you already knows me. For those who see me for the first time, thank you for being here. My name is Przemysław Roguski. Please feel free to call me Rogue. I'm principal security engineer at Red Hat, and today I would like to briefly present how proactive security work plays a key role in the trusted supply chain. Today, first, we will briefly talk about key differences between proactive and reactive security activities and how does the execution of this work look like today. Then I will show high-level implementation model for the proactive security activities in the Secure Software Development Lifecycle, SDLC, or Secure SDLC. When we know this, I will present how all proactive activities can be integrated as a part of the build pipeline based on the Red Hat example. And at the end, I will show two examples of the proactive vulnerability management and how AI can help with some of this work. There you go. So what is the proactive security work? It's a set of all activities that can be executed to test, verify product component before it's released to the customer. On this diagram, I listed the most typical one, activities like SAST scanning, DAS scanning, threat modeling, malware detection, including regression testing, and at the end, intentionally, I added product metadata verification to make sure that when you release product component, you know exactly what was released, when, what was included. I'm talking about SBOMs, CISA, VEX, and in the future, I hope OpenEoX as well. So how does execution of all this work look like today? Intentionally, I divided this to three groups: yesterday, today, and tomorrow. In the past, we were mostly focused on vulnerability responses. Today, we observe a big pressure for the shift left approach, where we want to do deep software testing and verification before that the software product is released. We want to collect as much as is possible information from the build process that ensures that our build was executed correctly, the build meets our security controls and our requirements, and it's released in a timely manner and insecure way. All that work is to make sure that everyone understands and follow the real risk-based security, not a security checkboxing. Okay, then what remains for tomorrow? For the future, we should work on a better automation and gating based on all of those findings that we executed the test during the build time to make sure that we can, for example, more precisely identify weaknesses and address them, remediate them before those weaknesses lead to a vulnerability when the product is already released to the customer environment. Let's take a look at all various security testing and their place in the Secure Software Development Lifecycle. On this diagram, I'm showing a suggested place for the security testing and verification in the specific SDLC phases, because we should know very well where the particular test is executed, where should be executed, to be sure that it's not executed too early or too late in the development process. On this slide, you can see that, for example, during the development phase that covers the build time, we execute SAST, DAST, SCA, malware scanners, and at the end, during the release, we ensure that the build product that we release to the customers is signed, and we verify the process, the distribution process, to make sure that it's distributed in the secure way. Great, that sounds really good, but that what is very important, we should make sure that all this proactive work should be executed as a part of the build and release process. It shouldn't be just a side process that is next to the build and release pipeline. We should make sure that security is built in a software supply chain. We shouldn't execute all those security controls and activities afterwards when the product is already released, because it's too late. Let's take a look how does look like in practice at Red Hat example. On this diagram, you can see how upstream code is used, ingested to the Red Hat downstream products. On the left side, there is an upstream code, then it's included to our pipeline, and during the whole SDLC phases, we test it, and then at the end, we know that it's security distributed to our customers. All this work is executed as a part of our product pipeline. So let's take a look at a little bit closer at the pipeline itself. Today at Red Hat, we are actively working on a new pipeline called Conflux, which is an open source, very important, open source, comprehensive build and test and release factory based on Tekton. Tekton is an open source cloud native CI/CD solution. Conflux is built around software supply chain security by default. Conflux meets the SALSA build level 3 requirements and produces necessary build 3 artifacts. SALSA stands for supply chain levels for software artifacts framework. As you can see, in Conflux, we can build, run various tests, including security scanning, and validate the content based on predefined rules during the release process. Let's take a look closer on the example pipeline. I hope that you can see it. It is an example pipeline starting from the beginning when we start the build to the end when the build is created. Every task in the pipeline is executed in a very controlled way and produce provenance data. There is no task that is just executed and there is no evidence what happened. We use Tekton chains, the Kubernetes custom resources definition controller that allow us to manage supply chain security in Tekton, together with Conforma. Conforma is another open source project that is used to validate predefined policy rules that we expect that particular build or builds must meet to be released to customers. Let's take a look at examples, 2 examples, how that validation looks like. In this example, we have a build with, various test results. One of the tasks does not meet the predefined policy rule. It seems that not allowed build base image was used. That's why that task was executed. The task status is successful. Result is that this specific task confirmed that this build was created based on not approved based image. In this case, this particular component as a part of the official product cannot be released to customers. Another example is here, where we see that all tests are okay, everything is fine based on our policy. There's only one test, CWE scan related, is related to the SCA scanner that was triggered during the build process. And this particular test has an alert, but it's not blocking rule. That's why still this build is okay, can be released to customers. But what we can do with this alert that we see in on this diagram, we found something. Should we ignore it, or maybe we should do something? This is where we have our proactive and reactive work, where we can use this information from the build time to improve what is on the other side when the product is already released. Let's see how proactive and reactive vulnerability management can work together. I will try to explain it. On the left side, we have all work related to the proactive part, the build time. On the right side, we have all work that is already on the reactive side, that is related to the already released content. So how we can work together? On the left side, we have a build. We scan it, we detected a CVE. And in this example, I would like to show two use cases. Let's imagine that this build is a new build. It wasn't released yet before. It's just a completely new component that will bring a new feature in our product. It wasn't released before. In this case, if we detect a CVE, it means that someone used affected library package, right? It's not published yet on, for example, Red Hat CVE pages because it's, again, new build. It wasn't released before. In this case, we have two options. We know that there is something, so we can block such build, do not allow it to release to production. We can tell the owner, hey, you have to fix it. New build will be created, it'll be scanned, everything is green. Now you can release it. And we don't need to do any updates on our public data. But there's another possible use case where the build that we just scanned, it's nothing new. It's just a new version, an update to the previous build that was already released. It's already used by many customers. We scan that build, we see vulnerability, we see that detected CVE, and we can compare that result to our public data. If we see discrepancy between what we found during the build time and what is publicly available on our CVE data, I'm thinking about Red Hat vulnerability database, then we can react accordingly to this fact. We can correct our data to make sure that everyone knows what is going on in this particular component. Still, we can block this build. We can tell owner, you have to fix it, and then release such update as a security update to this particular component. That will improve significantly our public data. That's one of the use cases how we can, execute proactive and reactive vulnerability management together. Another example is related to security activities, like I mentioned earlier, but in this case, SAST scanning. I hope that everyone are aware that SAST scanning results contain a lot of false positives. Trying to process all those scan results, it's very time consuming and not efficient. At the beginning of this year, at Red Hat, we did a POC where we combine SAST scanning results together with CVE data from the CVE records. And we try to find a pattern for exactly the same component and the same from one run product pattern between SAST scanning and what was already reported over the last year or years of the CVE records, the CVE data. And we found pretty interesting patterns that will improve and will help our engineering teams to focus on the right weaknesses, because it means that something is wrong if we found problems in our scan results and we repeat the same type of vulnerabilities again and again in this particular component. That will reduce number of reported CVEs against Red Hat portfolio. And of course, at the end, will improve the customer experience. Let's take a look how it looks like on the diagram. In this case, I divided this diagram by two, and when on top is what was already released. This is that reactive work and data that we have publicly available. On the bottom is build time, all tests that are executed as a part of the build process. Combining them together, of course, requires data standardization, because SAST rules and that how we have as a part of our CVE records, it's not exactly the same. So we need to first do a data standardization. And then we can use AI-based analysis to find the most typical patterns, and that will give us more precise weakness identification, categories of weaknesses, and will help prioritize the specific work and remediation. That could be also an input for more targeted threat modeling. I have a real example based on the analysis that was done. On the left side, there's a sorted SAS results for one single component in one product. On the right side is analysis of the CVEs for exactly the same component and the same product. And you can see after the data standardization that there are some patterns. We see that, for example, there are problems related to authorization errors, weakness category. So here we see that in this case, our engineering team, owner of this component, where we found this pattern, those patterns, should prioritize those three detected things first, because it's something that is repeating again and again. So let's address those problems to avoid new CVEs related to exactly the same problems again in the future. So we just discussed two possible use cases for proactive and reactive vulnerability management that can work together. I was pretty fast. Now we have time for questions.
Hi. Thank you for the presentation. Quick question. Isn't that a self-prophecy?
Can you speak a little louder? I'm not sure if it's enabled.
Isn't that a self-prophecy if we fix only those things that have been fixed in the past from the kind of vulnerability class? Aren't we missing out on those things that the product is vulnerable for, but those things haven't been fixed in the past? So if you go back one slide and you say, hey, I fixed that CWE, what is this, 283 or so?
284.
284, okay, close enough. I fixed that last couple times. I had 5 CVEs for that or whatever. But there would have been another CWE that comes up in the SAS every time. I've never fixed that before. I never start fixing that just because I'm always prioritizing other things. And so I'm trying to eradicate maybe an irrelevant class of errors that is not as important in my vulnerability, but I used to fix those with a lot of effort, and I could actually have better coverage or some others or fix more vulnerabilities easier if I just looked at the SAS test and looked at the severity of the vulnerability.
Very good question. So it means that, let me double check that I understand what we're asking for. It means that if I see in the SAS results repeating weakness category, but there was no CVEs related to that category in the past, and you're asking if I should ignore it?
It's not that I ask whether you should ignore it. It's more the question whether you do ignore it. And you know, if you prioritize other things over that thing that repeats, then, or maybe you have two different classes. One is always, and they have the same amount, and you have the one class, say the 284, that you always fix, and there's the other one, just pick a random number, I don't care, that has the same amount of findings in the SAS, but you have never fixed that before. So the question is, if I prioritize the 284 each and every time, since I fixed those before, and I never get to the point where I fix the other one, then it's more or less a self-fulfilling prophecy that I have that many 284s in my code, since I always prioritize them.
So that what I'm presenting here is one of ideas how we should better prioritize weakness remediation in our products. Only because I fix one CVE related to, or many CVEs last year, 2 years ago, whatever, related to this type of weakness class, it doesn't mean that I really remediated the problem. Because we see today that there are so many vulnerabilities reported every single day that many times owners of the product, instead of trying to find what is the problem, real problem, what is the root cause, they just want to, okay, let's just fix it. Let's just change one package, replace it, and done. Let's release it and done. Many times it's not a real root cause analysis and problem remediation. Is just, okay, let's just fix it, move on, because I have so many tasks to do, release new features, and the real problem is not addressed. That's what I'm trying to show here that, okay, we see that problems and patterns, so let's just prioritize some of them, because in SaaS results, there are so many different, things reported. There are so many false positives that it is really difficult to do, to remediate everything. As, for example, in this, on the left side, you see that SaaS results, and what was found that SaaS scanner suggested me that I need to fix weakness 398, which is a category. So what I'm supposed to do? So that's only one of the examples how we should prioritize the work, not repeating only the, okay, let's just fix the what was reported as a vulnerability, done, and next one. That's one of the possible approaches. But I agree, if something is repeating again and again in SaaS results, if I address the top priority, I can get back and find another patterns. What is repeating again? Then that's another prioritization step. Very good question. Thank you. We don't have remote microphone, so I'm sorry, you have to go there.
So this is a very interesting slide, and I'm curious if you had the chance also to look at other, I would say, metrics except the CV severity, like what is actually exploitable. So it has like exploit existing in Metasploit and ExploitDB, or maybe even like EPSS score levels, and maybe this can bring more, I would say more aspect of prioritization than just relying on the CVSS severity level.
Perfect question, thank you. Right now, as a part of this POC, we just focus to find out if we can find some kind of patterns. Based on that work, we found, okay, now we will just try to implement it. And definitely we need to add more metrics, not only severity, but also EPSS scoring and so on, to find out how we can improve this prioritization model, of course.
So you are planning to do it, or you have done it? I'm just curious to
right
see
now,
what the results.
No, that's what I'm presenting right now is a result of POC. It's not implemented in production. We don't use it today yet.
Thank you.
Hi. So I'm wondering, have you looked at the CWE distribution in the CVE system? Because I have a gut feeling that there are a lot of CWEs will be repeating, because I don't believe every CVE has a complete list of relevant CWE. CWE is not set up in a way that they're mutually exclusive, so that sometimes maybe multiple weaknesses are involved, but they're not all listed in CVE. So I actually don't know how CVE determines which CWE should be included in this case. So that's why I feel if you run a distribution, it might be that across the CWE, you feel, these 10 for all the CWEs, maybe these 10 CWEs always show up. It's like 90%.
Good question. It's also related to the CWE root cause mapping working group, where we have a strong push to make sure that always the CNA who assigned to report a CV, to assign the CV ID record, provides very precise information about the associated root cause, in this case, weakness that leads to this vulnerability. That's the very important first step, that you need to have a good metrics, good data on the CV side, information about weaknesses that leads to those vulnerabilities, to do this type of analysis. So here in this POC, I clean CVE records data, Red Hat CVE records data for the last year, 2024, to do this type of analysis. You ask also about the CWE chains, right? That are the question, that there will be more than one CVE,
Right.
CWE?
Right.
Yeah, so in this case, anyways, our data standardization is to make sure that we are not focusing only on one single CWE ID. We are focused on the CWE category.
Oh, okay.
Like it was said, category, weakness class. It's not only one single CWE ID, because if you want to do this type of analysis on the every single weakness ID, it will be really very difficult. Because over the time, for example, there could be a situation that you fix 10 CVEs related to a little bit different weaknesses, right? But all of those weaknesses are from the same class, like memory errors or something like that, or data validation. Then it means that you have something wrong in your code, in your application, in this area. All of those 10 CVEs were related to the different particular single weaknesses, but in total, all 10 were related to one and the same weakness class.
Okay.
Does it make sense?
Yeah, thank you.